Welcome to the afternoon session. Our first speaker is Suresh Nayak, and he will continue his series. He'll continue his series of lectures on residues and trace maps in Grothendieck duality.
Okay, thank you. So last time I gave some idea about how we construct this F-upper Schlick. So there were two approaches. One was a more constructive approach. So it's based on certain explicit formulas, and then we kind of put them together. So I'll briefly give the other approach also now, and then we'll go on to look at residues and trace maps. So this is the more abstract approach. It's more general, and it was initiated by Bellin and Verdier. So what I'll do is I'll just briefly mention the main results, and of course there's no way we can talk about the proofs. So here C is, again, just to remind you, category whose objects are Noetherian schemes. And morphisms are finite type maps which are separated. So the way this approach goes is we use the following results. So I'll just state the main results that we use. So one is no field. So it's just maps of Noetherian schemes. It's even the earlier approach, the first approach is also you don't need a field, but what you need is the presence of a dualizing complex on each scheme. And that puts some restrictions. It has to be universally catenary, and some other conditions will come in. And also, because of that, the duality is only, the theorem finally gets proved only for coherent complexes with coherent homology and quasi-coherent homology, which also arise naturally in many contexts. For that, you don't really have the duality theorem in some sense. Not completely, because if you are looking for a proper variety, you still have to do a lot of gluing. Because for a proper variety, you can't factor it as there are varieties which are not embeddable, as I mentioned last time. So you have to do local pasting, and so you have to construct a dualizing complex on an open cover, then glue them, and you have to have a coherent theory of dualizing complexes. Then you have to do some various things. So it doesn't quite simplify. No, even if you work over a field, it doesn't exactly simplify. It still remains quite complicated. No, there is no difference. No, that characteristic does not play a role. So this I mentioned last time. And so just to remind you once again that any map fx to y in C factors as x bar to y, where this is open immersion and this is proper. Okay, the next thing is the existence of right adjoints. So RF lower star. So for the time being, I am not putting the plus here, because actually you can prove the existence of adjoints without the plus also as a right adjoint. And as I mentioned earlier, this right adjoint is only interesting when f is proper. Otherwise, we are not really looking at the right adjoint. Anyway, so this was due to Deligne first. So Deligne proved it using some argument which ultimately goes back to, relies on the special adjoint functor theorem. And then later on in the 90s, Niemann gave a different proof using Brown representability. And this has an advantage of being a little more general. This one is using Brown representability. Just one case I would like to mention, and which is, suppose you have, so this is non-proper. Anyway, I have not put the properness assumption here, so this will not be exactly what we will use, but just to note that suppose I have, this is spec K. So let's say K is a field for the time, for simplicity. Then in this case, you can say what is F cross K. It's basically the Hom cross K is the Hom is a module associated to Hom AK. And you can see that this is not going to behave so well when you localize, because this term here, I mean, if you replace A by an open set, you get something different, slightly different. So this is if you have more than one, so this is of course an injective, the big module. It's an injective module, A module, and so in general, if you have more open sets, then what you have to do is you have to sort of do a similar thing over all the various open sets and build up a check complex like structure, and then that complex will be the. So in these affine, in this affine situation, you can write down explicitly what F cross should look like. If K is not a field, you may have to use some. Then it depends. I mean, you'll have to use an injective resolution. F upper Schlick, you'll have to use F cross. You'll have to use an injective. You'll have to replace this object by an injective resolution, and then for each injective again, you can do the same construction. And so in the affine case, you can actually explicitly write down what it looks like. Open base change theorem. So this is due to Deligne. It basically says that if I have let's call this F prime. And if I have this, so this is, let's say, I forgot whether you really need proper, but certainly for proper it's there. And then this is open. So you take a fibered square like this. Then what we have is F cross, and then I upper star is an isomorphism to the other way, J star F prime cross. So in other words, what this means is that, so again, to make it more precise, for any, so this is, for here you will probably need some bounded assumption. So for G dot belonging to D plus UCY, what we have is F cross G dot restricted to the open set X prime. And this is isomorphic to F prime, which is nothing but F restricted to X prime. cross, then G dot. That doesn't make sense, right? G dot, I have to do a star, so G dot restricted to X prime, Y prime. So this is an informal way of saying it, because upper star is just restriction. So what we are saying is that you take the adjoint over the restriction, that will be the restriction of the adjoint. So sorry. F cross, oh, sorry. Yeah. So using this, one easily shows that if we define F shriek to be I star F cross, sorry, bar cross, or F is given as X bar to Y. Okay, so for the factorization, a factorization of F, or I should say a compactification of F. Then F shriek is independent of the choice of compactification. So there's no unique way to compactify, and doesn't matter which one you choose. Any two of them will give you isomorphic answers. I mean, in some canonical isomorphism between them. And for that, if you try to prove it, you will see that, I mean, if you have this, then you can sort of come up with a proof. And a little more lengthy arguments, and more lengthy arguments give this kind of isomorphism. So here F, this is obviously for X, Y, Z, G. Etc. Meaning you have to check some associativity of these isomorphisms. So you have to set up a canonical isomorphism, and then you have to set up some you have to prove some associative rule. And so one has a theory of I will not elaborate on that statement. Basically, what I mean is that I have a functor F shriek for every F, and then it behaves in this nice way. So this theory does not rely on the looking at a dualizing complex and trying to glue them, and all those things are not there. Instead, it relies on these. I mean, it's not that these results are simpler. This is somewhat complicated, Nagata compactification, but these are, you've broken them into smaller parts, which in some sense could be done independently of each other. And one more thing is we also get sheafified duality. So the adjointness statement is about form, and you have a, one group on the left side, and then the other group on the right side. So now you can put them in sheaf form using R home dot. So you have RF lower star, R sheaf home dot, OX, sorry, yeah, OX, and then F dot, comma, F shriek G dot is isomorphic to R home dot OY, RF lower star F dot G dot. This is for proper, F proper. Because anyway, we are interested in it. We get an adjointness result using Shriek only for proper. But this is what I hope I didn't mess up here. The next interesting result is by Verdier, who generalized open base change theorem to a flat base change theorem. So again, a similar diagram, but now replace open by flat maps. Let me call this G, U, V. Then, okay, here again, I hope, yeah, there I mentioned proper and open. Here, let's put proper and flat. Then one can show, Verdier shows that you have a similar result, F cross, then B star, isomorphic to U star G cross. So using Verdier flat base change theorem, we can now sort of complete this theory almost. See, what this theory has done is we have given a construction of Shriek, but we have not computed anything. We have not said what it looks like on most examples. So the first important class of examples is smooth maps. We would like to see what we get for smooth maps. And that's not obvious in this abstract approach. So this is again due to Verdier. We'll call it the Verdier isomorphism. So it says that if F is smooth, let's again X to Y, smooth of relative dimension B, and this implies F Shriek is isomorphic to F upper star tensor with omega D F. So in the explicit approach that I talked about last time, we took this as a part of the definition. Now we sort of reverse the situation and we use these abstract results to set up a consistent theory here. And now we are saying that this theory gives us what we, one of the most important things that we need, which is that it has this. And I'll now sketch a proof of this. So the way the proof goes is, so sketch proof. Yeah. Everything, yeah, everything is happening in the derived category. Yeah, we will see. Yeah, you can explicitly write down what that isomorphism is, in the sense that, okay, we'll see the proof, and the proof will use various other isomorphisms, and then it's a question of how explicit or how comfortable you are with the other isomorphism. I mean, so we will use this, for example, and you can give a natural, you can give a map in this direction, and then that map is somewhat explicit, but it is in terms of adjoints. So it's obtained by looking at the adjoint of this map and doing something with it. But still, you can give a map in this direction here, and that's what we will use. And so this is a useful kind of trick that we keep using. So this is F and F. And so you can call this as pi 2 and pi 1. Then let's start with F shriek OY. I want to show that. So basically, since F is going to be flat, okay, so I will only sketch one part of the proof. Yeah, so once you know F is flat, it's actually is easy to show using projection formula kind of things, that you only need to know what is happening to OY. And if you show that, so if you put OY here and here, this just becomes OX. So it just gets cancelled off, meaning you are left with this. So the key point is to show F of a shriek OY is omega d FD. That's what we will show. We want to show this is omega d FD. So I'm going to tensor it with its dual. And its dual is lurking here because let's look at this delta. So then delta is a regular immersion. Locally given by d elements. By a sequence of length d. Length d. And then you can look at this I over I delta whole square. That's going to be free module over X over the diagonal of rank, sorry, not free, locally free module of rank D. And so you take its dth exterior power and I guess you dualize it. So this is the module which lives on the diagonal, and its dual is the module of differentials, the dth power, sorry. Its dual is going to be this one, this module here. So I'm going to tensor it with this one. And put it in minus dth spot. And this is isomorphic to delta upper star pi 2 upper star. So this is just identity. So I just appended this. F shriek OY tensored with, okay, so maybe one should give a smaller name, I mean a simpler name to this. So let's call this as n dot. It's I forget a normal, no? Normal module, the exterior power. And so this is F of a shriek OY tensored with OX. Yeah. And now this is isomorphic to, now if you do delta upper star of anything tensored with n dot, if you remember, this is actually delta shriek. That's one of the isomorphisms we gave, explicit isomorphisms we gave last time. I'm going to use one explicit calculation I made last time. That if you have a map which is given by regular immersion, then actually we can compute delta Schrieg for that. And the delta Schrieg is nothing but delta star tensored with this n dot module. And now I'm going to use base change. So this is going to be isomorphic to del Schrieg. Then this will become f star. Sorry, the diagram here. Sorry, this was. Okay, I wrote pi 2. Okay, that's confusing. Pi 2. So delta Schrieg, pi 1 Schrieg, f star OY. So this is by flat base change. And then finally, this is isomorphic to star OY, because del Schrieg, pi 1 Schrieg is is identity, and then this is OY. I'm ignoring some sign conventions here. So modulo all those sign conventions, what we get is OY is isomorphic to, so this was n dot dual, which is omega d f, and that is pretty much the main point. So this will be the inverse of this will be called the Verdier isomorphism. So this we will call as a Verdier isomorphism. Yeah. Yeah, x cross x over y. Yeah, that's the fiber product. This is a Cartesian square. Yeah, this was also Cartesian square here. Everything, all the squares drawn are so far Cartesian squares. Yeah. I delta is the ideal of the closed subscheme. The diagonal is going to be a closed subscheme. We assumed everything is separated, so the diagonal will be a closed subscheme, and the ideal shift. So this is a basic. This is a sort of a basic result that if you factor this identity map into this closed immersion followed by smooth map, then this closed immersion is locally given by a regular sequence. Okay, so that almost completes the Deligne-Verdier approach. One small result is there, which is not. Sorry, I shouldn't say small. It's not at all small. But one more last thing is there, which is that this isomorphism should also be pseudo-functorial, which is to say that if I have two smooth maps, then F Schrieg, G Schrieg should be isomorphic to tensor of the two omegas. So that can be proved, and there in literature already, but I will not elaborate on that. So that pretty much finishes the sort of the overall main results of the Deligne-Verdier approach. It gives everything that we are looking for, because it gives us a pseudo-functor which is localizable and which gives you module of differentials as its f upper Schrieg for smooth maps, and for proper maps you have the adjoint maps. So everything you have, and it's much more general because it works for any separated finite type map of Noetherian schemes. And the duality, the adjointness result also, oh, I forgot to mention here. Yeah, you need some assumptions on F, but those are not very big assumptions. So F dot, in fact, in this case, can be assumed to be in dqc of x, and G dot in dqc plus of y. And I think that's enough for this kind of isomorphism to hold. So it's fairly general, very less restrictions. The proof does use a lot of non-trivial results, But overall, it's slightly more modular, I think, meaning there are different components of the proofs which can be done independent of the other parts. That also makes it somewhat nicer. Yeah. Yeah, you get, no, I mean, we are just saying that the abstract construction will give you this model of differentials. That's all we are saying. The abstract construction is embed your smooth variety, affine variety, whatever, in some projective variety. Doesn't matter, that doesn't have to be smooth. Just embed it in some projective variety or proper variety. And compute the right adjoint and localize it, meaning restrict to the open set. Then on that open set, this will have, there has to be a natural isomorphism from here. That's what we are saying. So the right adjoint that we have constructed, restricted to that open set, will have to agree with the model of differentials. I mean, in a natural way. That is what we are saying. There is a notion of a dualizing sheaf. I will not have much time to talk about it. The dualizing sheaf is the first non-vanishing homology of f of a Schrick OY in general here, assuming, let's say, x to y is, let's say, yeah, I mean, I don't know. I think if you want to do anything interesting with the dualizing sheaf, it's better to have a few assumptions on the map. So you some equidimensional fibers, and some other things. Then you can look at the leftmost spot, and then the first non-vanishing homology will be called as a dualizing sheaf. So, for example, if you have a irreducible variety, then of dimension n, then in the minus nth spot, you will get the first non-vanishing homology. That will be the dualizing sheaf. And if it's not smooth, then it's not going to be omega d. Only on the smooth locus, it will agree with omega d. You'll have an isomorphism. Other places, it's a little more complicated. And people have given descriptions of what it should look like. But I will not talk about that part. Now we'll come to the last part of my, and this will be again slightly brief. So traces and residues. I'd like to go back to an example, what I was talking about last lecture. A couple of examples of residual complexes. So let's start with the simplest one, or the first interesting but simple one, x equal to spec z. Then you'll notice that the injective resolution of z looks like this. So that's your injective resolution. And then moreover, this breaks up into various parts here. So P is a prime. If you are interested in the sheaves, then you can put a tilde everywhere. This is affine, so it really doesn't matter so much. And these will be skyscraper sheaves. And this is the example of a residual complex because, I mean, this has coherent homology and it is having the injective hulls exactly in the right place. This is the injective hull of the residue field at 0, which is Q itself. And this is the injective hull at each point. And I leave it to check that exercise for students that check that. So if you call this complex as, or yeah, I mean, if you take f dot belonging to dc x, then f dot double dual is an isomorph in the derived category. Where double dual means, again, you can dualize with respect to Z as usual. So that is your usual dual, or you can, in this case, this is the injective resolution of Z. So you can dualize with respect to this one also. All right, so let's look at a similar example. So a similar thing will be true for any principal ideal domain. So let's take X is equal to, let's take a more global situation, P1K, where K is a field. And instead of taking the structure sheaf, I will take the module of differential forms. So take omega, and I'll call it, I'll think of this as a sheaf itself, so omega X over K. And analogous to what we have here, we have the following injective resolution. And this is, okay, I don't know what's a good way of writing this. So I'll use some ad hoc notation, omega. So this is the sheaf of meromorphic forms. So this is a constant sheaf. I don't know what's a good notation for this. And this is isomorphic to, again, direct sum of omega kx modulo omega x, sorry, in this case, I have x here. And look at the skyscraper sheaf formed by them. So, okay, so my notation is getting even more complicated. But okay, I hope you understand what I'm trying to say. So by abuse of notation, we will make sense out of this. And so this is just x belongs to x. So I'm switching between the sheaf and the, so this is the constant sheaf, but I will also use the same notation for the simply the module of differentials over the vector space kx over k. And this is that vector space modulo this local ring. Sorry, not local ring, this module. Sorry, I mean, yeah, it's a vector space, but it's also a module over the local ring. And this is a submodule of that, quotient out. It's just exactly like this. And you get these. So these are skyscraper sheaves here. And this is an injective resolution of omega x. Now, this being an injective resolution, our abstract theory says that also, since we have that Verdier isomorphism, we know that this is supposed to look like, this is isomorphic to f upper shriek k, maybe up to a shift. And so we know that there is a natural map. So let's call this as pi. Then we know that general theory tells you that you have a natural map. This is a co-unit map, pi upper shriek of omega x over k, divided by 1 if you like. This is the dualizing sheaf to k. So if you want, you can put this in, let's talk. So this will be in degree 0, and this is in degree -1. Because it's omega x shifted by 1, so it's one place to the left. And I know that there is a map of complexes like this. So if you apply, so pi lower star is just global sections. So if you apply global sections of this, you will simply get the same underlying module here, and you'll get these modules. So you have a complex like this, and you are supposed to get a map to k sitting in degree 0. So the question is, what is this map? You have a map of complexes in the derived category from here to here. So I claim there's an honest map here from here to here, and of complexes, and we'll describe what this map is. I didn't say anything about K. So K could be an algebraically closed field, or K could have some algebraic extensions. So these points may not be k rational. Their residue fields might be larger than k also. So the answer will be that at each, okay. So first let's make a little bit more identifications here. In fact, if you look at it, this is actually isomorphic to local cohomology of omega xx over the local ring. If you want, I can put mx here. And that's because from the local ring to get to the residue field, you have to just invert the local parameter. And that's exactly how this local cohomology will be computed. And if you want, you can go one step further and put a completion here also. All right, so the claim will be that these individual maps will be residue maps. And when you put them all together, this diagram will commute. That is actually coming from the co-unit, which is also called the trace. And the fact that the diagram commutes will tell you that for any meromorphic form, the sum of all residues is 0. So those are the two interesting statements reflected in the existence of this map. So just to repeat, one is that these maps individually will be given by residues. And the second is that the fact that there is a commutative diagram like this will tell us that, in fact, the sum of all residues of a meromorphic form is 0, which we know in the extended complex plane. And but conversely meaning 0, yeah, meromorphic form, yes. So correct. So that is all captured here. So I will now go on to elaborate on this further and describe these maps. So to do that, we have to talk a little bit about representing elements of local cohomology modules as fractions, which I think has already been talked about. I'll just very briefly remind you. How do we represent an element of where M is an R module and I inside R is generated, if you want, up to radicals by D elements. Let's say so that essentially goes back to looking at local cohomology. Sorry, I used D, so let's put D here. Then we can calculate this as of R gamma IM, and I think it was mentioned maybe in John Greenleaf's talk that this is also the infinite or the stable Koszul complex on A tensor over Rm, which is, then we look at direct sum of M AI direct sum of M, AI, AJ, and so on and so forth with appropriate differential maps. And the last one is M A1 to AD. And so what this will tell us is that any element M can be written, and we will write as so this is what is called as a generalized fraction. And this represents the class of M over A1. Okay. Maybe I should put some, I should allow indices, I guess. So I1 to IN, I1. The point is that, so why bother writing it like this when it's actually just a fraction? But the point is that if you interchange, for example, two of the AIs, it will induce a sign change. So you have to be a bit careful. And so this element per se should not be thought of as representing the class. It is this one. This is sensitive to the order in which you write down the AIs. And there are rules for what happens if you change the generators. So if you choose a different set of generators, if you do not just linear change of generators, but other change of generators also, if you do, there are some rules about how to manipulate these fractions. So it's better not to look at this element. This element represents a fraction or this choice of this sequence of generators. But if you change the sequence, somewhere D became N. Then we'll write it like this. Okay, so with this setup, we can now talk about some explicit formulas for trace maps in certain cases and residue maps. And then we'll say that this also is compatible with the abstract theory. Why are the Verdier isomorphisms? So the abstract theory has all these things like traces and all. We want to transport those traces to this concrete module omega d. This is how we are approaching the theory. And so we'll try to understand what it is doing to this in this setup. Some concrete or explicit formulas. So one of these we have already seen last time in special cases. So one of them was start with P and Y. And this we saw last time by an explicit calculation. There exists an isomorphism. We gave it a name, integral pi from Rn pi lower star omega n pi to OI. And if you want, you can put a shift here and then get rid of the Rn. And you can, in fact, this is the same as actually giving a map from R pi lower star omega n pi shifted by n to OY. And that's because you can show that there is no other cohomology. So you'll have to show that the only cohomology that comes is in the nth degree. and all other degrees there's none. So therefore, giving this map is the same as giving this map. And we saw that there is an isomorphism like this last time, or we gave a sketch proof. Not even a proof, maybe we just give a sketch argument. It's some standard thing you can find in various textbooks. Then let's so this is the other situation, Tn or Td, Tn, and let I is equal to T1 to Tn. So then there exists a residue. So we'll define this map, residue map. Is an A-linear map from Hni omega. So here I have to use omega hat n R over A. R is basically too big over A. So if you just look at module of differentials, that will give you something terrible. But if you complete it, then it turns out you will still get a finitely generated module, or the other ways of describing this module. But let's assume that we know what this means. So this is basically a free R module generated by dt1 to dtn. And take the local cohomology of this. Then the residue map is a map from here to A, an A-linear map, uniquely determined by the following properties. Formulas. So I want to take a typical element here, but I'll break down that typical element, and so I will just give what is happening for only some sort of fractions, and those fractions are of the form dt1, use t1, yeah, dt1 wedge dtn, because that's the nth form, and then the generalized fraction has denominators coming from here. So here I'll put t1 to the power I1, en to the power in, and this will go to 1. Yes, ij is equal to -1 for all j. So basically, when it is -1, -1, -1 all the way through, and it's 0 otherwise. So in one variable, it's just dt over t goes to 1, and dt over all other powers of t, dt times any other power of t goes to 0. And this will take care of everything, because any other element in the local cohomology is some element f from the power series ring and some fractions here. So you can, okay, so these you can expand f as a power series, and you can cancel. Okay, so there are some rules. So if I, for example, multiply by t to the power ti to the power some a, then you can cancel off. If there is a common factor, you can cancel them off. And if any one of them happens to be the unit element, meaning if in becomes 0, then this fraction becomes 0. So there are some rules about these fractions. And so if you don't like the fact that I'm implicitly using those rules, then you can just say that f of t1 to tn, this power series times dt1 wedge dtn, t1 to the power I1, tn to the power in. You can figure out where it should go by simply looking at coefficient of I guess maybe I'll make a mistake there. So f of t1 suppose this is the one. If it exists, otherwise anyway, it's going to be 0. Meaning if any of the ij's are 1, so ij's are all non-negative, and if any one of them becomes, 0, then, or in this case, if it becomes 1, so that after subtracting 1, it becomes 0, then it's just 0. So, what am I saying? Sorry. No, what I mean is, if it is T1, then it should be 1. Yeah, that's what I mean. I think this is correct. Okay, so with this, so this is some concrete calculation. We have not brought the abstract theory into picture here. We could have done this in the beginning. I mean, without knowing what is Grothendieck duality, we can, okay, this one maybe, even this, yeah, even without knowing what is Grothendieck duality, this is something very explicit, and we can set up this isomorphism, and we can set up this map here. But what is the relevance to duality is that duality is predicting that there's a trace map here on the left-hand side, and we are giving an explicit isomorphism. So via this isomorphism, that trace map should correspond to these things. And so that's the theorem. The theorem, there are many more theorems like this, but in some sense, this is one of the results. So theorem. Sorry, forgot to switch off my phone. No, there is no isomorphism. It's not an isomorphism. This is very big. It's killing most of these fractions. Only some fraction is going to 1. Almost all fractions are going to 0. It's just an A-linear map. Which one? This one? No, it's not. I mean, this one is free module, but I have put local cohomology, so then it is not, it's something else. I mean, then it's a 0-dimensional module. In fact, it's going to be the injective hull at the residue. It's going to be isomorphic to the injective hull at the residue field. It's actually a huge module, not finitely generated. Okay, so theorem is that these concrete formulas, this is a recent preprint. Okay, so I mean, these formulas are known for all the experts in duality theory. I mean, this is not a surprise. And everybody sets up their own set of definitions and tries to use these formulas. What we are trying to say is that the abstract theory predicts these formulas in a very natural way via the Verdier isomorphism. So the Verdier isomorphism in a natural way gives these abstract formulas. So the claim is not so surprising, but it's just that we are giving a streamlined approach to the whole thing. So the theorem is that the above concrete formulas, so it will be vaguely phrased, and that's because a precise statement would be too long. So the above concrete formulas are induced from abstract traces, which is basically co-units of adjunctions, via the Verdier isomorphism. And here I will sneak in one notion here. Okay, let me complete it and you'll see. So this is over schemes and formal schemes. So I have to introduce, we have to talk about formal schemes. Before lunch, Strickland, Neil Strickland also mentioned that. So basically, this is a complete ring, and it is somehow easier to deal with this and think of this as a algebra over A. If you look at, instead of looking at the spectrum of A, you should look at the formal spectrum of A. The formal spectrum of A is all those points, all those primes which contain the defining ideal T1 to Tn. And so in that sense, as a topological space, it'll just look like spec A, because these are all ideals which contain this, all the T1 to Tn. But as a sheaf of rings, it will be obtained by looking at the ring R or completion of the localizations of R at various open sets. So we have to use, so it's better to deal with formal schemes, because as a formal, if you look at the formal spectrum of R, it will become proper over A, even though they both look like affine and it's not a finite map. But as a formal spectrum of R is going to be proper over spectrum of A. And that is kind of technically useful, because for proper maps, we can talk about adjointness. So here I have sneaked in this thing, and this is there's more to it. Namely, one can do a lot of Grothendieck duality for formal schemes also. We can essentially, whatever outline I have given earlier, except for Nagata compactification, which is not available for formal schemes. Everything else, like existence of right adjoints, flat base change, open base change, all those results, and therefore Verdier isomorphism. All those results just follow the same approach. They work for formal schemes also, provided you have the right notion of finite type. So finite type means you have to go modulo the defining ideal and then check if it's a map of finite type of rings and so on and so forth. So there is a whole theory for formal objects, which is formal spectrums of complete rings, rings which are complete with respect to some ideals. And one can, except for the Nagata compactification theorem, everything else is available. And so one can define a theory of shriek and traces and all those things for whichever map can be factored as open followed by proper in the formal sense. So whichever maps can be factored, for those you have a theory of shriek. So we'll pretend that we kind of are comfortable with that in the same sense that we are already seen for schemes. And I will use that. It's just to indicate that the proofs are somewhat similar, what you do here and what you do here, but not quite, but they are somewhat, I mean, it's a similar idea. So let me very briefly mention for example, how does the first isomorphism come by? So what do I mean by this is the abstract trace actually gives you exactly this. What we mean is the meaning of the statement is that suppose, for example, if X was E and Y, then the assertion here is the following. Look at R pi lower star omega n pi lifted by n. So I'm not going to use that isomorphism. Instead, I'm going to use Verdier isomorphism. This is why Verdier. Then I'm going to put R pi lower star pi shriek OY. And then I know abstract theory gives me an adjunction. And I have this. And the claim in this theorem is that this map is exactly the integral map, the very explicitly constructed integral map. These constructions do not require any Grothendieck duality. You can just do it any first course in algebraic geometry or commutative algebra. So these explicit, that explicit map can be obtained by this process. This is the co-unit. So this is what we prove. And similarly for the second one is a little more complicated, and I will still mention it because we need to just very briefly look at what is the formalism for residues. And so the second one, it roughly goes like this. So let's take, maybe I'll do it there. So take this factorization. Then as map of schemes, this is spec A. This will be what is called as formal spectrum of R. I have a map here. This will be a closed immersion because it's given by vanishing of an ideal. This will be, so let's call this as, give it a better name. So let's call this as X, let's call this as Y. And I have again Y, spec A. And this will turn out to be proper in the sense of formal schemes. So it's usually called pseudo proper. Or maybe in this case, it's actually proper. Okay, no, never mind. Pseudo proper. So if you call this map as I and this as F, then what we are saying is the local cohomology module can be thought of as R gamma Y, RF lower star, omega hat, N X over Y, squared over N. Okay, you can call this F. So the only extra thing I have done is I have put this here. And that's corresponding to the local cohomology. Then this is this actually has a natural map. Get rid of the R gamma Y, and then you just have RF lower star omega hat N F shifted by N, which is isomorphic to RF lower star. And then I have what I would like to call as shriek, but this is shriek in the formal world, and we really have not said much about its construction. And then to OY, this is the trace. So this is your local cohomology module, nth local cohomology because R gamma which supports nth local cohomology of this module. And this is an affine map, so you can drop the R and just think of it as lower star, which is just giving you the sections, global sections. And we are saying that we have a map to A. This OY is actually just A tilde. And the claim is that that map is again so here again there is some Verdier being used. As I said, there is a Verdier, there's an analog of the Verdier map for in the formal setup also. It's the same proof. Once you have all the correct definitions of shriek and all the correct base change theorems and everything else, then this is what you get. And the claim is that this map is exactly the concrete map here. The concrete map, very explicit map, is already given here. So what we are saying is that via the Verdier map, the abstract traces will induce, the abstract co-unit maps will induce these very concrete maps like this for projective space and for this complete ring here. So why only stick to projective space? So for other smooth varieties, we don't really have a good set of global coordinates. So to talk about an explicit map, one has to do some more work, or one has to set up some more elaborate theory. Locally, however, if I give you a smooth variety, then its local ring, its completion is always going to look like this if you are working over a algebraically closed field. And so this does capture what is happening locally, at least over an algebraically closed field, or when the residue field is the same as the base field you started with. Okay, I'll try to finish up fast. So with all this, I should very briefly mention here that we can do this kind of residue in a more general setup. So I will not write anything about it, just draw a few diagrams. So more generally, you can have what is called as a, and this does show up when you are looking at non-algebraically closed fields. So you can have an arbitrary map here, and this is so this is a finite flat map. And in this setup, I would like to say that there is again some sort of a residue formalism. But here, what you do is to employ the residue formalism or to do something analogous to what we have done here. So here, this is a special case when Z is equal to Y and you have a section. That is what I think is happening there. And you can assume these are affine. Yeah, this was the same as this. So that's a special case. But slightly more general is when you have a finite. For example, think of a residue finite extension. So you have a field K, and then you have a closed point whose residue field is a finite extension. And in that case, also you can do something similar. What you have to do is not work with this map, but instead look at its completion. So this is x comma, okay, x hat. I will just say x hat, where this is completion along the closed subscheme given by Z. And then look at Y. Then this will turn out to be proper. Just like what happened here, this map turned out to be proper, meaning pseudo-proper. So pseudo-proper. And then you just apply the same kind of thing, and you can develop, you can write down a residue map, or you can give the abstract theory predicts the existence of something which should look like a residue map. So what do those residue maps look like? If it is, if the residue fields are the same, then the theorem is saying that it looks like this. It looks like this map. But if the residue fields are not the same, then it's slightly more complicated. So what comes into play is simply the trace of the field, the trace of the field extension. So there are a bunch of formulas which tell you how to manipulate these residue expressions. And due to lack of time, anyway, I was not planning to write down all of them, but there are a couple of them I want to mention, and one of them will be relevant to this situation. So two of them, so these are residue formulas. Due to Hartshorne, I think. And they are called R1 to R10. Hartshorne actually never wrote down a proof of them, and I think Conrad is the one who first gave a proof of that. And he uses the earlier theory of using dualizing complexes to prove these things. So we gave an we mentioned that these, or not mentioned, we proved that these things can also be derived from this abstract theory. And let me mention two formulas. So one of them is R4. So R4 says the following. So this is called transitivity of differentials. So if you have x to y to z smooth, then, and these are all smooth, then something like residue, okay, I guess we have to introduce some. So I never wrote down, we didn't put a subscript there, but now because we have different maps, we need to put some subscripts here. So let's call it residue y over z of residue x over y of alpha T1 to Tn. So here, okay, let's call it Te, and then beta. And this is S1 SE, but this has the expected form, which is that is equal to residue of x over z of alpha wedge beta, and then 1 to E, S1 to S2. So this is one such formula. This just says that, there's a natural way of combining the model of differentials here and model of differentials here. And the Verdier isomorphism, if you use it, and the trace maps, abstract trace maps, if you use them, it will be compatible with this kind of thing. So there's no surprise here. And this is the one I wanted to mention what will happen if you take a point whose residue field is not quite K. So you start with K, but you take a point whose residue field is not K. So let's take, it's the same situation there. Sorry, I'll just take 2 minutes. I think time is up. Just please give me 2 minutes. So X to Y. And I have finite flat. So think of this as a field, and this is a field extension, and this is some variety which has a speck of that field extension as one of its points. So this is smooth, and this is a closed immersion. Again, I didn't explain all the notations, but TIs are, yeah, I mean, so sorry, same thing will appear here also. So TIs are a bunch of parameters here, which give you, with respect to some closed subscheme, which is finite and free over Z, and similarly there is a SIs will give you something here. So a similar situation here. What we want to say is that, okay, yeah, there are two formulas. Let me mention both of them. So for any phi belonging to gamma x OX, we have residue of phi dt1 wedge dtr, where t1 to tr, so Z is given by, Z is the zero locus of zeros of t1 to tr. Then this is this over t1 to tr is equal to the canonical trace of over Z over Y. Canonical trace means the usual trace map, but okay, yeah. So what? Okay, since this is finite and flat, okay, I will also assume these are affine. So this is some spec A, this is some spec C, if you like, this is spec B. So you can think of this as spec A, spec B, spec C. Then C is finite, so it's a projective module over A, and therefore you can talk about the trace and the canonical trace. The canonical trace is the usual trace for a projective module, multiplication by an element, because C is a ring by itself, multiplication by an element of C induces an endomorphism of C over A, and just take the trace of that endomorphism. So that's a canonical trace of phi restricted to Z. But I feel it's the other formula which is more interesting. And so let me write that. So let's specialize to the situation where X is a polynomial ring. So maybe I'll just write the rings. So the rings are A and A. Use T1, yeah, A T1 to Tn. No, I don't want to use the same T1 to Tn. So let's call this X1 to Xn. And then this C. So what, okay, I forgot to mention this, somehow something, so Tate has something to say in this context. Basically in this context, I guess, this is going to be or at least in this context, it's a relative complete intersection over this one, right? And so the C will be, so the dual of C with respect to A will be actually isomorphic to C as a, I mean, it will be isomorphic to C as a C module. But the canonical trace may not be a generator of that. So what we get is, in this case, the following. If you look at, you call this phi, and you look at F1 to Fn, kernel phi, then sorry, so this is the last thing I'm going to write. Then residue of dt1, I call them x1, sorry, or f1 n is, I guess the fi's are nothing but these are pi's. And this is 1. So more generally, if you put some polynomial here, then you will have to put the image of that polynomial in C, pi of f. So for example, you can take a inseparable extension and see what happens. If you take, for example, if you have a field K and you take K adjoint and there's an element A and you have a to the power 1 by P here, then you can put AT and then T to the power P minus A will be in the kernel. So you will have dt here, but I mean dx. So x to the power P minus A will be in the kernel, dx, but this will be x to the power P minus A. So dx or x to the power P minus A go to 1. So this is how the trace is moving. So there are many such formulas, but essentially these are the formulas, and that is what these individual maps are going to look like. And the fact that some of the residues is 0, you can first check when K is algebraically closed, then it's some straightforward calculation. And in general, you can prove it using some general theory. Okay, I'll stop here.
Any questions? Comments?
To use the abstract trace formalism and abstract Verdier formalism to say that everything is, see what you want to, okay, somewhere in the picture, you want to say that it will turn out that these residue maps are compatible with the trace maps. Well, sorry, these maps are compatible with this one. For example, there will be a natural map from local cohomology at a point to of the same omega to this one, and then r pi lower star to OY. So I mean, if you put an R gamma of a point here, then you get a map from here to here and then to OY. So the concrete trace and the concrete residue are closely related. What we want to say is that the abstract theory gives everything. But if you want to say the abstract theory gives everything, how do you lay your hands on the residue map? On the trace map, you can lay your hands by just using Verdier and the abstract formalism. But for the residue maps, you need something. You need a proper map in picture. And that proper map is not a priori available to you because you're just looking at some local cohomology. So you're just looking at something like this here. So yeah, so when you go to proper formal, when you complete it, then it becomes proper. So this is a priori an affine map, but if you think as formal schemes, it's proper. So then the abstract theory is available. You can talk about trace maps and everything. The lower star functor will have a right adjoint for general reasons, and that right adjoint will have therefore a co-unit map. And that's a trace map, and that will be compatible with this. I mean, there's also a map from x. I mean, x to x, this x hat to x. So you can relate the global trace and the local trace, the residue map and the global trace map if it is proper. And so there are various things you can, various games you can play to. If you want to prove that kind of theorem, you need this some sort of compatibility, and that is where having a formal scheme in hand. Yes, it's a completion of x with respect to z. This may not be proper, but this is necessarily proper. If you assume this is proper, this is finite. So, I mean, I'm not saying you need formal schemes, but formal schemes gives one convenient way of doing things. Otherwise, you have to do some compactification, and then you have to show independence of the construction with respect to compactification. So that gets into its own things. So if you have a theory available for formal schemes, might as well use it. And that makes it easier. That is the point. It's not indispensable.
Any other questions?
No, there are small manuscripts which talk about generalized fractions. So for example, there's one Lippmann student had a thesis which starts from just nothing, rings, modules, and he just describes what is a generalized fraction. Each out, yeah, within a few pages. Yeah, I can tell you the reference. Okay. Yeah, so he does it from scratch. So. Sorry? Developed what? I'm not sure. He has used it a few times.
More questions? Okay, if not, then let's thank Suresh for this wonderful series of 4 lectures.
Thank you for your patience.